So what is temperature a measure of? It's of the movement or motion. And what is motion? The measure of the average kinetic energy of the particles in a sample of matter. So temperature is the measure of average kinetic energy. On average, how fast are each particles moving and vibrating? We got 3 different temperature scales. In actual science classes, we do not use Fahrenheit. We use Kelvin or Celsius. Kelvin is the preferred scientific measure or scientific unit for temperature. So Kelvin and Celsius are the same thing, except for Kelvin is shifted over. So if you were to increase the temperature by 1 degree Celsius or 1 Kelvin, it's the same measure. If you were to increase by 10 degrees Celsius, you would also be increasing by 10 Kelvin. Note that Kelvin isn't in degrees. Celsius and Fahrenheit are. So in order to convert between Kelvin and Celsius, you just add 273 to Celsius. So water boils at 100 degrees Celsius. In Fahrenheit, that's 212 degrees Fahrenheit. And if you want to convert Celsius into Kelvin, if you want to convert Celsius into Kelvin, you just add 273. So 100 plus 273 is 373. So water will boil at 373 Kelvin. Note there isn't supposed to be a degree symbol on the Kelvin because Kelvin isn't degrees. This picture's slightly wrong. Water freezes at 32 degrees Fahrenheit. In Celsius, it would be 0 degrees Celsius. Again, if you wanted to convert Celsius into Kelvin, you just add 273. So 0 plus 273 is 273. Kelvin, the reason why Kelvin exists, the scale for Kelvin, or the temperature scale Kelvin, is because it actually starts at 0. If you use Celsius, you can have negative values. So absolute 0, the coldest possible temperature ever, would be negative 273 in Celsius. But there is no negative temperatures of Kelvin because we begin at starting at 0. We then have thermal energy. Thermal energy is the total energy of the particles in the material. This includes the kinetic energy from the motion of the particles, but also includes the potential energy, the forces within or between particles due to its position. It depends on temperature, mass, and the type of substance. So every substance is structured differently. Again, it measures the potential energy, so so the bonds between. And Thomas, put your mask on properly. Amanda, do you have your mask on? Sorry, your hand was covering it. Just checking. I said I couldn't see your mask. Your hand was covering it. Just checking. So, water, for example, has very unique bonds. It actually has a lot of energy in it because of how the water molecule is situated. Metal bonds in a unique way to where there's actually less energy between the bonds. So How quickly does it take to boil water? How quickly is it does it require to heat up metal? So so if you put your mouth on so if you put a pot of water on the stove and you start heating it up, do you think it would all be heated to the temperature of the fire in a minute? It takes a long time to heat up water. Now then, if you put something, a metal pan into the oven at 400 degrees Fahrenheit, how long do you think it would take for that thing to get super hot? Uh, Probably a minute, depending on how much metal you put in. If I put something into the oven that's metal, I would not reach in there and grab it after 1 minute. However, if I put water in the oven and then pull it out, I would probably not expect the water to heat up very much. Water requires a lot of energy to heat up, whereas metal doesn't take that much. So the amount of thermal energy required to heat something up not only depends on the kinetic energy, but meaning temperature. It also depends on the potential energy from it. So thermal energy not depends on temperature. It also depends on mass. So how much material. For example, if you try heating up a cup of water versus a gallon of water, you would expect the cup of water to heat up faster. Also, the type of substance, whether it's metal or it's water or it's glass, all factors in. So we have 2 beakers of water. They're at the same temperature. They're both at 80 degrees Celsius. But which one has more thermal energy? Again, they're at the same temperature. Which one would have more energy, A or B? Why? More mass. So more water means more mass. So again, thermal energy depends on the mass, the type of substance. In this case, they're both the same water, same temperature, but the mass is different. So we would say that B has more thermal energy just because it has more mass. Heat. Heat is the thermal energy that flows from a warmer material to a cooler material. Heat always flows from hot to cold. So heat is just the amount of thermal energy that flows from one object to another, and it always goes from a warmer object to a colder object. Like work, heat is measured in joules. Heat is a form of energy. It is actually a transfer of energy. It's energy that is being transferred from one object to another. Question. Why does things feel hot or cold? Is it because they're hot or cold? So how we feel temperature depends on two things. One is psychological. For example, it's usually always the same temperature in this classroom. However, as y'all notice, some days it feels cold, some days it feels hot, but the temperature of the room doesn't really change. We have a thermostat that sets the temperature to 70 degrees Fahrenheit, and it regulates that temperature to where it's almost very constant. We feel temperature. Well, let's see. Why does A feel hot and B feel cold? But why specifically will we feel that A is hot? Again, that's almost boiling water, and that's almost freezing water on the right. So what did I say heat was? A transfer of thermal energy. So how is heat being transferred when you hold A? Exactly. We would feel heat flowing from container A into your hand. If heat is flowing into you, we feel that as being hot. It doesn't necessarily depend on temperature. Usually things that are hotter than your hand, heat can only transfer from hot to cold. Whereas in B, since your body temperature, I think is, let me look that up in Celsius. What is your body temperature in Fahrenheit? 98.6. It's not. It's 37 in Fahrenheit. I mean in Celsius. In Celsius, it's 37. So your body temperature is 37. So if you're holding something that's 10 degrees Celsius, heat will flow from your hot hand, relatively hot, into the cold material because it's at a lower temperature. So without doing this, and Michael, lift your head up, no sleeping. Without doing this ahead of time, I want you to predict something. Is your desk the metal leg? Don't touch it yet. But is the metal portion on your desk and the wood on your desk at the same temperature? Yes. They're at room temperature. Is something heating it up? Both of it's still in the light, right? You're correct. Your desk might be slightly warmer. But now I want you to touch the metal and then touch your desk. Which feels colder? But it's at the same temperature. But no, the metal should feel colder. Why does it feel colder? Yes, that is the exact reason. Heat is able to absorb heat. Metal is able to absorb heat faster. So when you touch metal, you feel heat leaving your hand at a faster rate. Our brain tells us that we're losing a lot of heat very quickly, so it should feel cold. When we touch our desk, there's not really much heat flowing away from our hand, so you might feel it as not very cold or not even feel a temperature at all. Depending on, you do have some plastic on it, but usually wood. There is a plastic or wax coating on your desk. But if you touch the plastic, maybe of your seat, you don't feel much heat leaving your hand as quickly. So versus the metal, and the metal you should feel heat leaving very fast. All we feel is how much heat is either going into us or out of us. There is a psychological thing. If you constantly go around saying it's cold, you can actually make yourself feel cold by just saying it. And if you constantly say it's hot, you can actually make yourself start sweating due to this perceived hotness. It could be freezing outside and snowing, and if you lie to yourself and say it's really hot outside, you can force yourself to start sweating and make yourself believe that you're hot. There is a psychological component, but for the most part, what temperature you feel is how much heat is entering or leaving your body. So, another thing is your skin warms up. If you're outside in the sun's going to warm up your skin. And when you walk into this room, all the heat on your skin is going to leave out until you equalize. So when you first walk in, you'll feel that heat leaving and thus feel cold until you get used to the temperature.
I meant like when you know what, like say you can tell my body to do anything.
Yeah.
Even if you know that it's hot.
Oh yes. There's also one other thing that majorly affects temperature. It's moisture. So remember, water can absorb a lot of energy. So humidity can, and Thomas, wake up, head up, don't be laying on the desk. Humidity, so how we cool our bodies off, if you don't know this, is we sweat. Even if you don't see the water on your skin, we're constantly giving off small bits of sweat. As that evaporates, it carries heat away from us. But if there's too much water in the air, it prevents our sweating from cooling us off and we feel a whole lot hotter. It's the reason why in Texas, when it's 90 degrees outside, we're very, very hot. However, if you were to go to a dry desert and it be 105 degrees, it would probably feel better than in Texas at 90 degrees. That's because there's no moisture in a desert. So, we also have specific heat. This is the amount of energy required to raise the temperature of 1 kilogram of a material by 1 degree Kelvin. Sometimes we'll also use specific heat to where it references 1 gram instead of 1 kilogram, because a kilogram is 2.2 pounds. Usually we measure it in grams by 1 degree Kelvin or Celsius. Note that if we're talking about a change in temperature, we can use degrees Celsius or Kelvin. And this is technically incorrect. You don't use degree symbol with Kelvin. So make sure that you remove that word degree. It should be by 1 Kelvin. We never use the degree symbol with Kelvins. Need to edit this PowerPoint later. Yes. Yes. So, we'll see in this class, it actually takes a tremendous amount of energy to heat things up. So to heat up 2.2 pounds or 1 kilogram of water requires 4,184 joules of energy. And that's only by 1 degree Celsius. So if you had 2.2 pounds of water or 1 kilogram of water, to heat it from 10 degrees Celsius to 11 degrees Celsius takes 4,184 joules of energy. That is a lot of energy for something so small. Also, notice how much bigger water is compared to everything else. We see metals like aluminum, iron, copper, and silver have very low specific heats. Water requires a lot of energy to heat it up, whereas copper and iron take very little. So which sample will take longer to heat to 100 degrees Celsius? 50 grams of aluminum or 50 grams of copper? So which would take longer? Aluminum. So you have to add 920 joules of energy to heat up 1 kilogram of it, whereas copper only requires 380 joules of energy. K stands for Kelvin. And again, if we're referring to a change in temperature, you can use Kelvin or Celsius. Yes.
Okay, so if you leave like a coat can outside and like put up the bottle in there, would it evaporate or no?
Like if it's sealed up?
Yeah.
No, it can't penetrate the plastic and metal. I don't know if y'all know this, but the inside of a Coke can is plastic. So, Coke can, acid.
Greetings, fellow nerds. Time for some really simple and fun chemistry. So we all know
So
that
this has very concentrated acid.
In this video, however, we're going to do the opposite and remove the can from the drink and show there is a little known plastic liner inside
So
the
they
can.
melted away the metal.
To do it is fairly simple.
Plastic
First,
doesn't dissolve in acid.
and using sandpaper,
That's the reason why we store acid in
can.
plastic containers.
The label does more than just brand the can. Now
So he scratches off the paint.
I tried to use 5% vinegar, but it didn't seem to work. As usual, I should warn you that hydrochloric acid is corrosive and you should wear gloves when handling it. Anyway,
so it's dissolving away the metal.
As it reacts, the acid dissolves the aluminum can and produces
It's
aluminum
too
chloride.
dangerous.
This is how we're removing the can without touching the coke.
A single drop
now,
would eat through your skin.
Carefully lift the can from the acid. And there is the coke. The aluminum can is gone. So how is the coke
it's now
staying
plastic
in the
at the bottom?
Plastic liner on the inside of the can. It's put in to protect the drink from leaching metals out of the can. Now
so, if you ever heard the expression that a can of Coke or a can of something has a metallic taste to it, it's never touching metal. Because the reason why is you do not store drinks in metal containers because it can get a metallic taste. And consuming metals is bad, as you can get something known as metal toxicity. So what they do to prevent it from ever touching the metal is they coat the inside of your metal can with a very thin layer of plastic. Yeah. That's clear plastic. It's clear. You can't really see. It's almost like a waxy surface on it. If you ever cut up in a can, you can actually feel the plastic layer. So aluminum has a higher specific heat. Thus, aluminum will take longer to cool down or heat up. This is also why people who live next to the ocean or large bodies of water, it usually stays warmer there because the water takes a long time to cool off. Which brings us to the equation we're working on. Note, this little triangle is the Greek letter D. It's called delta. So you might have heard of Greek letters like alpha, beta, zeta, and we have delta. This is just the Greek letter D. If you're curious, y'all know the name of our alphabet? What's the name of our alphabet? What alphabet do we use? So think back. What are some really great countries that have existed? Or languages too? So Rome. And what language did the Romans speak? Latin. We use the Latin alphabet. So we use the same letters as people who speak Latin used to use. Greek predates it. So here's the Greek letter D. So No, they start over time, just like y'all have been doing. People get lazy. Sometimes instead of so usually you go down, you go over, and then you connect back up. Eventually, some people got really lazy and started turning the triangle more sideways. And then they got ultra lazy and they started curving the triangle. And then when you see, eventually this triangle over time start looking more like a rounded D shape. So note that this was the original letter D, but because of laziness of people writing, they eventually rounded the corner and straightened it up, and we eventually get a capital letter D. Once John gets back. I will say. So this letter here is delta. It's the Greek letter D. Capital letter D. And it means change in science. So if I were to write delta T, what this says is, so this is delta T. This means change in temperature. So that would be final temperature minus initial temperature. Thomas, keep your eyes open and pay attention. Everyone good? So here's the code word. So we use the capital letter Q to represent heat, and it's measured in joules. Our mass is going to be measured in kilograms. Change in temperature, again, if it refers to a change in temperature, we can use Kelvin or degrees Celsius. And change in temperature just means final temperature minus initial temperature. And then specific heat, we use C with a lowercase p next to it. That's just the symbol meaning specific heat. And that's measured in joules per kilogram Kelvin or joules per kilogram degree Celsius. Heat will either be negative when heat is lost or positive when heat is gained. So depending on the order of your initial versus final, I will like to note, a lot of y'all do this. I'll bring that back up. A lot of y'all do this. So what's the difference between 4 and 2? With this being initial and this being final. Yeah, what is the difference? See, again, y'all are still doing it. -2. For some reason, you choose whichever one's larger. In science, we have a formal definition. The difference is final minus initial. The final was 2, so 2 minus the initial is 4. 2 minus 4 is equal to -2, not +2. So order is important. Again, I see it over and over. You guys tend to just choose whichever one is larger and subtract the smaller from it, so you always get positive. Direction is important in science. We always take the final and minus the initial from it. So if we're going from a high temperature to a lower temperature, our heat is going to end up being negative. Everyone good here? And Michael, it's your mask. And not Michael, Thomas. I'm very good at not confusing you. And even though it's very inappropriate, if anyone watched the South Park special, y'all shouldn't watch it. Y'all are underage. But did y'all watch it? They make fun. They make fun of people and call it chin diapers. And it showed in one scene of South Park, a UPS driver comes in and someone answers the door. It's like, sir, I'm sorry, due to COVID, I can't deliver this package until you put your mask on or your chin diaper on. And he goes and he literally straps it under his chin. Oh, thank God. Here you go. Like literally just strapping it under his chin. Now we're safe. I'm like, what's the point? But now every time I see someone without covering their mouth and nose, I'm like, chin diaper. So we have a very scientific instrument. It is 2 coffee cups stacked on top of each other with a cover. Very, very scientific. It's called a calorimeter. You can get more fancy and actually design a better calorimeter. But actually, 2 coffee cups made out of styrofoam is actually very good. It's a device used to measure changes in thermal energy by having it well insulated. So the purpose of styrofoam is to prevent heat from transferring. And put up your phone, John. So styrofoam is an insulation. So styrofoam is a type of an insulator. It prevents heat from transferring through it. Yes, but I wouldn't use styrofoam. I'd use something better. Something that wouldn't break and crumble. More like a foam that could spread out over the surface. Like insulation foam. But technically you could use styrofoam to do it. But however, it can't fill all the cracks and won't be as good. So it is an insulated system. The styrofoam does insulate. And you can actually measure heat gained and heat loss. Note, conservation of energy, so heat is a form of energy. Energy can only be transferred from one object to another. So the same amount of heat being gained by the liquid is the same amount of heat lost from something else. What this means is if you drop in ice into water, the amount of heat the ice gains is equal to the amount of heat lost by the liquid. The heat is being transferred from the liquid into the ice. So technically, when you put ice in your glass of water, you're not making the... it's better to say that you're warming up the ice rather than cooling off the liquid. In order to warm the ice, heat has to flow from the liquid into the ice. Yes. So let's do some examples. A 32-gram silver spoon cools from 60 degrees Celsius to 20 degrees Celsius. How much heat is lost by the spoon? So this is in grams, not kilograms. Does anyone know how to convert grams into kilograms? Divide by 1,000. So we're given that the mass is 32 grams, the initial temperature is 60 degrees Celsius, final temperature is 20 degrees Celsius. What is, and the specific heat of silver, if we were to go back on the table, you can see silver is 235 joules per kilogram. Note that since it has kilograms in it, we need to use kilograms. So our equation is heat is equal to mass times the change in temperature times the specific heat. So 32 divided by 1,000 is 0.032 kilograms. What is the change in temperature? Negative 40. Again, you can't just choose the largest number and subtract the smallest from it. It's final minus initial. You should be getting a negative number in this case. So we plug those values in. Again, degrees Celsius and a Kelvin are the same thing whenever we're referring to changes in temperature. So degrees Celsius and Kelvin cancel each other out. The kilogram and a kilogram cancel each other out. The only unit that stays is joules. So we get a negative value here. Negative 301 joules. So again, the Kelvin and degrees Celsius will cancel each other out because we're dealing with a change in temperature. So this is only valid if we're working with a change in temperature. If we're just dealing with temperature by itself, we have to use Kelvin and science. So the negative heat means that it's lost, that heat was lost. So if it says how much heat is lost by a spoon, you would expect a negative answer, and we got that when doing the math. So how much heat is required to warm 230 grams of water from 12 degrees Celsius to 90 degrees Celsius? So our initial temperature is 12, our final is 90, and our specific heat is 4,184 joules per kilogram Kelvin. Again, we have our equation. We need to convert mass into kilograms. So remember, if we are not in meters, seconds, or kilograms, you're going to have to convert it. And how we convert grams is simply dividing by 1,000. So our final was 90, our initial was 12, so we subtract and we see that our change in temperature is 78. We plug it in, and we get 75,061 joules. We can actually vary depending on how much. So, like a water bottle is 500 grams of water, roughly. So the water bottle I've been drinking is 500 grams. So you can expect over 100,000 joules of energy when boiling it, needed to boil it. So let's work on some examples together. So recall that heat is equal to mass times change in temperature times specific heat. So this is your heat, which is energy, and it's measured in joules. We have our mass, which is measured in kilograms. We have change in temperature, which is measured in degrees Celsius or Kelvin. And our specific heat which is either in joules per kilogram degree Celsius or joules per kilogram Kelvin. These two can be interchanged for this formula only. So the specific heat of liquid water is 4,184 joules per kilogram degree Celsius. How much energy, and this will be heat, how much heat energy is required to heat 500 grams of water that is at 30 degrees Celsius to its boiling point of 100 degrees Celsius. So this is the mass. This is the initial temperature. Note that temperature uses a capital letter T. Time uses a lowercase t. This will be our final temperature. And this will be our CP. So mass, and we need to convert it, is equal to 0.5 kilograms. Our initial temperature is 30 degrees Celsius. Our final temperature is 100 degrees Celsius. Thus, our change in temperature would be just 70 degrees. And we're looking for Q with a CP of 4,154 joules per kilogram degree Celsius. So Q is equal to mass times change in temperature times CP. We can expand that already. Mass times final temperature minus initial temperature times CP. So that would be 0.5 times 100 minus 30 times 4,154. Your bottle of water, when it's full, is roughly 500 grams of water. Does anyone have a bottle of water? How many milliliters of water does it contain? So what do you think 1 milliliter of water weighs? 1 milliliter is equal to 1 gram for water. So doing this, we see that it requires 146,440 joules of energy. So if you were to dump a water bottle content that's at 30 degrees Celsius, so roughly like 80 degrees or something. Let's see. 30 C to Fahrenheit. That's 86 degrees. So this is 86 degrees Fahrenheit. So if you had 86 degree Fahrenheit water and you wanted to boil it, get it to 212 degrees Fahrenheit, you would have to supply 146,000 joules of energy. That is a lot of energy. Luckily, though, fire produces a lot of energy. There's a lot of energy stored in the chemical bonds, and when you burn a gas, such as natural gas, it generates a lot. It's also why the most expensive thing in a house to run is your AC and heater.